Good morning, students. I, Sadaf Khan from the Millennium School, South City, welcome you to this session of chemistry. Students, we have been discussing the chapter Structure of the Atom, and I have been talking about new concepts. In our live sessions also, we have talked about different models, the classical models and the discoveries of the subatomic particles. And then we were discussing a concept where we had stated that light, which is an electromagnetic radiation, exhibits dual behavior. It has a dual nature, and by dual means two, we meant that light, an electromagnetic radiation, can behave both like a wave and like a particle. And the wave behavior was justified or proven by the phenomenon of diffraction and interference as shown by the electromagnetic radiation, that is light. And the particle behavior was concluded that light, which is an electromagnetic radiation, exhibits particle nature because of these three effects that were explained because of the particle nature of the wave, that is the black body radiation, photoelectric effect, and the atomic spectra. These two I have already explained to you in detail in our Zoom session also. And this, some students wanted more about the atomic spectra. That is why I am sending this video across to you. Now, coming to the atomic spectra. Students, what is an atomic spectra? Or how does an atomic spectra rise? An atomic spectra is formed due to an interaction. Basically, any atomic spectra is formed because of the interaction between light, that is an electromagnetic radiation, and matter. Matter could be molecules, atoms, ions. If we are talking of atomic spectra, then we talk of atoms, interaction of light with the atoms. And how does this pattern or the spectra arise? We know that when a beam of white light is passed through a prism, then this white light, which has 7 components or 7 colors or 7 wavelengths, it splits into its 7 colors. That is, a pattern is obtained on the screen, that is a continuous pattern of 7 colors is obtained on the screen, and we know that it is the Vibgyor. So this is how, when white light is passed through a prism, it gives this pattern, that is Vibgyor. And this light, which is an electromagnetic radiation, and white light, which is just a very, very narrow band. I have shown you the atomic electromagnetic spectrum. We have seen how widely ranged it is, and white light is a very, very narrow range in this electromagnetic spectrum. This narrow range is between 400 to 700 nanometers, and this pattern that you get is a continuous spectrum when white light is passed through the prism. It is a continuous spectrum. So coming to the atomic spectra, students, when white light interacts with atoms, ions, or molecules, when white light, which is electromagnetic radiation, interacts with atoms, molecules, or ions, that is matter, then there is association of radiation that takes place, leading to the emergence of an atomic spectra, leading to the formation of an atomic spectra. So this atomic spectra is observed because of the interaction between white light and matter, that is atoms, molecules, or ions, and there is association of radiation that takes place, and an atomic spectra is observed. This atomic spectra is of two types, an absorption spectra and an emission spectrum. First, I will talk about absorption spectra. Absorption, we have been talking about this term, very, very commonly used term. When we study the absorption spectra, before this, talking about in detail about the absorption and the emission spectra, students, let me tell you how these spectral studies are carried out in the lab. In the lab, basically, there is a very, very sophisticated instrument that is known as a spectrometer, and that instrument is used to study these spectral patterns of different atoms, molecules, or ions. And the study is known as, the study of the spectral pattern of different atoms, molecules, or ions is known as spectroscopy. Now, if you get a chance to visit any of the CSIR labs, let me tell you there are 4 CSIR labs in Lucknow. That is NBRI, National Botanical Research Institute, CDRI, Central Drug Research Institute, IITR, Toxicological Research Institute, and CIMAP, that is the Medicinal and Aromatic Plants Research Institute. These 4 institutes are located. They have infrastructure facility, the central infrastructure facility. They have the in-house facilities where you can see a wide range of instruments, and one of them is spectrophotometer. It is a very, very expensive and a highly sophisticated instrument kept under very controlled conditions, used with a lot of precautions. So the instrument that is used to conduct these studies is known as a spectrophotometer or spectrometer. Now coming back to the absorption spectra, how is the absorption spectra obtained? White light is passed through a cold gas. Here you have to mention this word cold because we are talking about de-excited state, unexcited molecules. So this cold, the temperature is low, the molecules are not excited. When you heat any molecule, it absorbs the heat energy and it gets excited. That is why when white light is passed through cold gas, this cold gas molecules, some of the molecules of this cold gas are going to absorb some radiations from the white light, some wavelengths from the white light. Why? White light has 7 wavelengths, so some of the wavelength is going to be absorbed by the molecules of this white light. Some portion of the white light is absorbed by the gas and the rest is emitted in the form of absorption spectra. Now this is a very, very crude attempt at explaining, demonstrating absorption spectra. You can look for a better image in your books, it is given, and also you can go to a link, I will send it to you. You can see in that link you can see the very, very beautiful images of absorption and emission spectra. But nevertheless, just to explain you, I have made this attempt. So how does an absorption spectrum look like? Absorption spectrum, basically there is a continuous colored background, as you can see, a continuous colored background of the 7 components of the visible region. These are the 7 components of the visible region, from the vibgyor to the red. All the 7 components, there is a continuous bright background, and against this continuous background you can see some dark bands over here, dark, very, very sharp lines over here. Now what is this telling us? What do you understand from this? You basically understand that when this white light, which had 7 wavelengths, was passed through this cold gas, some of the wavelengths were absorbed by the molecules. So when they were absorbed by the molecules, the emitted radiation did not lagged those. Basically the emitted radiation lagged those wavelengths or lagged those components of the white light that were absorbed by these molecules, and the component or the wavelength of the white light that is absorbed is absent in the spectrum, and it is seen as dark bands. That is, absence of the wavelengths that are absorbed by the molecules are seen as the dark bands against a continuous bright background. Now coming to the emission spectrum. Here you can see an emission spectra is possible only when an atom is in the excited state. Now this is a major difference between absorption spectra and emission spectra. Absorption spectra, an atom was not in the excited state, it could absorb energy. We had taken the cold gas molecules. Here an emission spectra would be possible only when an atom is in the excited state. When an atom is in the excited state means it possesses some extra energy as compared to the ground state, and that is why after absorbing that extra energy it has reached to a higher energy level. Excited atoms, as I have been telling you, the relationship between energy and stability. Excited atoms possess extra energy, and because they possess extra energy, they are not stable. Why they are not stable? Because stability is inversely proportional to energy. Higher the energy, lower will be the stability. So if the energy is high, stability would be low, and excited atoms have high energy, hence they are not stable. Now to stabilize, it is the natural tendency of any object or any particle to be in their stable state, to attain stability. That is the natural tendency, and it is a universal rule. So to stabilize themselves, they have to lose that extra energy. They reduce their energy by emitting radiation. So extra energy is lost in the form of radiation, and this radiation is emitted by an excited atom, and the emitted radiation is known as the emission spectrum. So here we see, as on contrary to the absorption spectra where we had taken the cold gas, here it is the hot gas. Why hot gas? Because we have given heat energy to it, it has absorbed energy and it has gone into the excited state. It has excited atoms or atoms. Hot gas has excited atoms. These excited atoms will lose some energy to come back to the ground state to attain stability, and this energy that is lost or emitted will result in the formation of the emission spectra. Also now, at the contrary to the absorption spectra where you could see dark black lines against a continuous colored background, here you see there is a continuous dark background, black background, and some colored lines, colored bands you can see over here. Now this is, as I told you, in the absorption spectra. What was absent in the absorption spectra? The wavelengths that were absorbed were absent. The wavelengths that were absorbed by the gas molecules were absent. That is why those dark lines were there on the continuous background. In the emission spectra, all the other wavelengths have been absorbed. Only the ones that are emitted are we can see in the form of the colored bands against a black background. Okay, so only the emitted wavelengths in the form of colored bands are seen against a dark background. You can take a look at the example of the atomic spectra, helium spectra. You can take a look for your reference, and you can compare. You will see exactly the wavelengths that are missing in the absorption spectra are the wavelengths that are emitted in the emission spectrum. Now coming to the atomic spectrum of hydrogen. Hydrogen is very widely studied in great details because it was a very simple atom. A lot of studies have been done on this, and this study was particularly important because this progressed the findings from atomic spectra to atomic structure. So how atomic spectra is used to establish the atomic structure or led to the establishment of the atomic structure, the atomic spectra the studies conducted on atomic spectra were very, very important. Now students, please keep this in mind that atomic spectra is unique for an atom, and because it is unique for each particular atom, it is used to identify the atoms. Because of this characteristic of uniqueness, it is used to identify atoms. Now, there was a scientist named Balmer. When the emission spectra of hydrogen was observed, then certain wavelengths were seen in the emission spectra, and they tried to find out the wavelengths. They tried to work out which wavelengths are emitted. And one such finding was done by Balmer, and he gave an expression which is 1 upon lambda, or the wave number, and after conducting a lot of studies he came to this expression, which is 109667 per centimeter, because it is 1 upon wavelength per centimeter, 1 upon 2 square minus 1 upon n square, where n is an integer, that is 345. Please note it is not 2 over here. I will explain you why. This wavelength, this electromagnetic radiation that was identified by Balmer, and he worked out this experiment, this radiation was particularly known as the Balmer series in the hydrogen spectrum, and this was just one of the radiation that was studied by Balmer. Similarly, there were studies carried on by Lyman, Bastian, Brackett, Fund, and so on. One more I have not written over here, that is a very, very recent finding. I will let you know. So Lyman was another. He also worked out the expression and identified another wavelength in the hydrogen spectrum, and they gave the expression 1 upon 1 square minus 1 upon n square, where n is an integer, that is 2, 3, 4, 5. Apart from 1, it would be 2, 3, 4, 5. Balmer, I have already told you, n is an integer, 3, 4, 5. Bastian, another wavelength series that was observed, which was n 1 upon 3 square minus 1 upon n square, where n would be 4, 5, 6, and so on. Bracket series, n would be 5, 6, 7, and so on, and P fund would be 6, 7, and so on. So these are the lines that were observed in the hydrogen spectrum, and these are the names of the scientists who had given expressions for these lines that were observed, or the lines or the wavelengths that were observed in the hydrogen spectrum. Now Rydberg just generalized this expression. Rydberg, I've talked about in my earlier lectures also. Rydberg had generalized this spectrum where 1 upon lambda is equal to RH. He gave this as the Rydberg's constant, 1 upon n1 square minus 1 upon n2 square, where you know that n1 and n2 are integers. Now making the picture more clear, these expressions more clear, you can visualize it like this. Now this is, if you study a hydrogen spectrum, this is the nucleus. These are the different energy levels. That is the orbits in which an electron can revolve around the nucleus. These are the different energy levels. N1, the ground state, then N2, N equals to 3, 4, 5, 6, so on, and it could go up till infinity. Now, we all know that electrons, when they are in their normal or the ground state, then they occupy N equals to 1. Upon absorption of energy, suppose an electron goes to N equals to 7. Alright? An electron was in N equals to 1. Upon absorption of energy, it goes to the 7th shell. Now, from here to here, there is just one route. It will go like this. Right? But from here to here, it could follow several routes. Alright? So, when Lyman did his studies, he conducted his studies, he observed that an electron, when an electron comes to the ground state, that is N equals to 1, here you see N1 was 1 and N2 was 2, 3, 4, 5, 6 and so on. So when the electron jumps from higher energy levels, that is here 7, 6, 5, 4, 3, 2, when electron jumps from higher energy level and comes to the first shell, then the series of the wavelength observed, then the wavelength electromagnetic radiation observed is the Lyman series, and it falls in the UV region. Then if it comes to the from the 7th, 6th, 5th higher energy levels up to the second shell only. See, it is not coming here till the N equals to 1, it is just coming to the second shell. Then this series is known as the Balmer series, and the wavelength is emitted in the visible region. Likewise, when it comes to the third, it is the Paschen series, and the wavelength is emitted in the infrared bracket. It is N equals to 4, N1 is 4. Okay, so it is in the the wavelength emitted is in the infrared region, and for N equals to 5, N1 equals to 5, again it is wavelength is emitted in the infrared radiation. So by this diagram you can understand that these different series were obtained when the electrons from the higher energy state could return to the lower energy states, and when it returned to the first shell, it was the Lyman series. To the second shell, it was the Balmer series. To the third, it was the Paschen series. To the fourth, it was the bracket series. And to the fifth, it was the P-Fund series, as I have already written over here. So in case of Lyman, N1 you can see is equal to 1. So that is why I have written 1 over here. In case of Balmer, N1 is equal to 2. In case of Paschen, N1 is equal to 3. In case of bracket, N1 is equal to 4. And in case of Fund, it is N1 is equal to 5. So this is how the studies were carried on and these are the different series of the wavelengths that were observed and calculated for in the hydrogen spectrum. So this is all about the hydrogen spectrum, students, that you should be knowing, and I will continue with the next concept in the next video. In case of any queries, students, please feel free to message or ask. But don't let your doubts remain, otherwise it will become very difficult for you to move ahead smoothly with the chapter. Thank you so much.